students, and she has asked why is it that she cannot see the line of the intake in the two-stroke engine. There is, in the diagram, if you see, there is no time when the pressure is at atmospheric inside the cylinder. That is why you do not have air coming in at atmospheric pressure to show a line that it is starting at zero. If you see the timing diagram of the two-stroke, let me see. Boys are still coming in. That's why I have to keep admitting them. I cannot move off from the screen. Let me see. Let me just keep, don't go away. Huh? No, I don't have the diagram here. Okay, I'll have to go back to the old PowerPoint. Now, how do I go back to? Actually, I have a new laptop now, and the sound system is much better than the previous one. So I'm getting a little more familiar with it. And Sarthaki, I will get your diagram. If you get that diagram out in front of you, the two-stroke timing diagram. If you see where there is
Yes, sir.
the inlet port and exhaust port, the exhaust port opens first when the piston is coming down, because the exhaust ports are located above the inlet ports. That is why when the piston is coming down, the exhaust gets a passage to leave. And as the piston goes down further, the inlet ports open. So then the pressurized air comes into the cylinder and pushes out the exhaust gases. So the process of scavenging, process of filling up the cylinder is partly when the piston is coming down and partly when the piston is going up again. When the piston crosses the bottom dead center and moves upwards, it first closes the inlet ports again because it has to be symmetrical. The location of the inlet ports and exhaust ports are all exactly at the same height as when the piston is coming down or up. So that is why the angles are also very symmetrical. So when the piston starts moving up, the air is still coming in at a pressure above atmospheric. So there is no atmospheric line as such shown in the two-stroke PV diagram. But in the case of the four-stroke, you will see the pressure because the atmospheric air is entering into the cylinder and coming in to the intake stroke. And thereafter, the compression starts. Then again, during the exhaust stroke, it is below or rather near about the atmospheric line. I'll have to refer to the diagram. I'll come to that after the class once again. Satyaki, you pay, stay on alert. Okay.
Yes, sir.
Now, we will
Yes, sir.
continue where we left off in the last class. In the last class, I had given you this diagram. No, not this one. Here, this one. And I told you take a screenshot and make a hand sketch so that anytime you're asked to explain the parts of a two-stroke crosset type of engine, you will be able to draw this diagram. This is a reasonably easy diagram and has got all the names of the parts very evenly distributed. So once you know the names of the parts, it becomes very easy to explain the engine. If you don't know the names of the parts, then it becomes very difficult. So the importance lies in knowing your engine components. All right. So this is your two-stroke engine. And I think before we go into the four-stroke or medium-speed engines, I'd like to show you a video on two-stroke engines by MAN. Unfortunately, the commentary on the video is not being able to be transferred to you. So that is something I will keep explaining while the video is on. Let us start the video right from scratch. All right. I don't know what to do, how to get the sound across to you. I can hear the sound, but unfortunately, you're not able to hear the sound. Okay, this is the two-stroke. That's a turbocharger, what you see there. Right now, it is covered. It is covered with a cloth so that no dust and dirt comes in. It is not in the running condition, but I don't know why he's got it covered here. It should be open. And this engine is not running. This is just background sound. This engine is running because you can see it running. This is the flywheel. What you see is the flywheel. Is the video commentary audible to you?
No, sir.
No, sir.
Oh, I
No,
don't know
sir.
how. Because it is an explanation on the total video how it is working. Is the picture clear to you? Is the video picture clear to you?
Yes. Yes, sir.
Okay, only the video. How do I get the sound across to you? What does it say? Show menu for subtitles. Okay, at least the subtitles will be there.
Yes, sir. That will help, sir.
Okay, audio subtitles, two subtitles. The video, two channel, two channel. What is this now? How do I choose the video? Subtitle file? No.
Sir, I think there are no subtitles for this video, sir.
Yes, I think
The
so.
file is empty. Yes, sir.
Anyway,
So
I'll
the
try to
file is
explain
empty,
it.
sir. Yes, sir.
Because what is this
Because
now?
what is this now?
Editing photo.
Editing photo.
Play in mini view. Show more options. No, 30
No,
degrees.
30.
What is 30? Skip forward. No. Okay, never mind. Let's have a look at the video. Actually, what you see is a two-stroke engine, and he's explaining to you how the crosshead is, how the piston has a long stroke, where the stuffing box is. These are very clearly shown. So let us proceed. Exhaust gas temperature pressure gauge, temperature gauge. This is the exhaust valve. This is the exhaust valve. This is the piston with the piston rod. It is fixed to the piston. These are the inlet ports. These are the inlet ports. This is the stuffing box. This is the crosshead. And the crosshead is going in the two guides on the two sides. And that is the connecting rod, which is making angularity. This is the crankshaft. See, that's the other web over that side. And this is in this chamber. You see, this is the stuffing box which separates the under piston spaces with the crankcase spaces. All right. This is the exhaust passage. This is the exhaust. These are the fuel pumps on the side. The gas pressure acts on the top of the piston to force it downwards, and the force travels along the piston rod. Force travels along the piston rod to the crosshead, and then it is put in an angle. Then it goes at an angle. All right, this is the force is transmitted to the angle, and then the crankshaft is made to rotate. So then it results. So because it is going at an angle, there will be a force on this side. So there is a transverse force. One force this side, one force this side. So there will be a force on this side. See, this is the force. So this is the crosshead that is supported by four parts. This is the piston which is fixed to the rod. This is the long stroke engine. This is a piston. This is how he is putting the piston rings in place. This is the device which helps in pulling out the piston ring to a certain level. If you stretch it too much, then it will get a permanent set. This is a special tool to remove the piston rings or put back the ring. The piston is put now upside down. This is the piston rod, and that is the this is the bed plate, and this is the crankshaft. It is so big that it is made in two pieces, and then they are joined together. This is the turbocharger which is going to supply the air. This is the air, scavenge air. Scavenge air goes inside. This is the scavenge manifold. And this is the firing of the in cylinder, and the gas pressures are acting on top, and the piston starts going down. Then the air comes in from it and pushes out the exhaust gases. Again, compression takes place. This is a two-stroke engine, remember. And the air pushes out exhaust gases. This is the exhaust. Air is again compressed. And see, that volume of air is compressed to small volume. So you can imagine how dense that air is, and the fuel has to penetrate through the dense air. The scavenge air enters and pushes out the exhaust gases. So that is the entire two-stroke, long-stroke engine. You see the piston rod, how long it is. This is to avoid the fouling of the liner when the angularity is made. Yeah. Now here is the diagram. Okay. Sastaki, now pay attention. See, there is no atmospheric line because by the time that it comes in, the pressure already starts rising. It is partly on when the piston is coming down and partly when it is going up. So when the piston is coming down, it is coming through this upper line and it comes to the BDC. And then when it starts moving up, then you have the pressure already in the cylinder and the compression starting. So this is the diagram for the two-stroke engine, and the area enclosed by this diagram is indicative of the work done. If you see at this point, the pressure is, the gradient is much faster. This is the point at which the exhaust valve or the exhaust port, depending on the construction of the engine, that opens. That is why you have a much more sharper drop in pressure from this point. Otherwise, the entire line from along this is actually the expansion line. And at this point, there is a sharper line of drop, which shows that the exhaust valve or exhaust port is open and the exhaust gas initially starts moving out. And in the process of moving out, it crosses a lower pressure inside the cylinder. And that is the time when the inlet port opens and the atmospheric air comes into the chamber and fills up that space. In the process of filling up, the exhaust gases are discharged. So that is why you don't see a horizontal line because it's a two-stroke engine. And within the stroke of expansion and compression, the air is filled into the cylinder and the compression starts. That is why you have a diagram like this for the two-stroke, which is quite unlike the diagram in the four-stroke. All right, let's see a little more. But after this,
Yes.
I'll be stopping it a little bit.
Excuse me, sir.
Yes, what is it? Yes,
Sir,
go ahead.
this is Cadet Siddharth.
Okay.
This graph can also be used for determining the position of the piston in the liner.
This diagram can be used for what?
Sir, to determine the position of the piston in the cylinder
Yes,
liner.
absolutely. He is already showing you the position of the piston. You see how the piston is traveling at the bottom. This is exactly what the pressure is when the piston is in this position. Again, let's go back. All right. Okay, let's see it again. Exactly. What you're saying is absolutely true. The position of the piston will also indicate the pressure at that particular point. Okay. Now look at the bottom diagram and then look at the
Sir.
pressure diagram. I wish the sound was available to you. Yes.
No.
See, now the piston is moving and based here, this is the pressure when the piston is here. So exactly where what the pressure is inside is indicated by that. That is why he has shown you this diagram. This is the expansion. It will open the ports. You see, at this point, 1 minute. Okay. See, this is the point where the compression is taking place, all right? And I will stop it again when it comes here. And that is the point when the exhaust valve will open. Now compression is going on. And near the upper dead center, the pressure rises very rapidly. And now it is expanding. As it expands, that is the point where the exhaust valve will open because there is no exhaust port. So exhaust valve opens means the pressure drop has a sharper gradient. This diagram is not so clear, but the diagram I have given you earlier in the first PowerPoint will indicate the rapid drop in pressure because the exhaust valve opens when there is still some pressure above the atmospheric inside the cylinder. So moment the exhaust valve opens, or in the case of an exhaust port, when it opens, there's a rapid rush of the exhaust gases outwards. In the process, when that mass of exhaust gas move out, there's a region of depletion where it was. And that is the moment when the inlet port is opened and the atmospheric air will come in if it is normally aspirated. But most engines are supercharged, so their pressure will come under a much higher pressure than atmospheric. So that air coming in will immediately start pushing out the remaining exhaust gases. So this process takes partly during the downward stroke of the piston after the inlet port and partly during the upward stroke from the BDC up to the inlet port. So this part of the movement is partly when the piston is going down and partly when it is going up. All right. Now again it will go. What happened? Yeah. The expansion. You see the piston, how it is traveling and how the pressure lines are made. Okay, a little more. Yes. This is the passage for taking the readings. This is where the measurement of power is used. You see, he's using a very modern technique, but this is now going into the 6th semester program. Indicator clock, and he's got an electronic device where all the measurements are taken at various positions. So it's purely a digital technology now being utilized. Okay, now this is going into our 6th semester area. So we will put a stop to this, and that is what you have seen of a two-stroke engine and how the parts are working. That was my intention, to show you how this engine is working. You saw how the crosshead function moving up and down, and it enables the connecting rod to swivel at the same time rotate at the bottom portion. Okay, now you saw the stuffing box, how it seals the scavenge spaces against the crankcase spaces. The oil for the cylinder liner is totally different from the oil that is used in the crankcase, and under no circumstances must the oils intermix or get contaminated by each other. Normally, cylinder oil is more likely to come into the crankcase because excess or whatever cylinder oil is drained out falls into this space. And if the sealing is not satisfactory, it may come into the crankcase and contaminate the oil in the crankcase. Remember, for satisfactory lubrication, the most important property of the lube oil is the viscosity. So this viscosity is a parameter which is decided by the designer of the bearing or the machine, that this particular viscosity oil has to be used. And based on that, your choices for the lubrication is made. For a turbocharger, the lubricating oil will be bearings is different. For the governor, the lubricating oil is different. For the crankcase, the lubricating oil is different. And sometimes for the turning gear, the lubricating oil may be different. So in one engine, you will have 3 or 4 different lubricating oils that are used. You cannot interchange one with the other. It will fail. You see, there's another issue that is not there in this PowerPoint. I'm going to point it out to you. Most of the machines are rotating machines. All right. So you have something that is rotating in a bearing. And to enable this bearing to be lubricated, the principle of lubrication is hydrodynamic lubrication. Hydro means a fluid, dynamic means motion. So motion of the fluid in the shaftings arrangement is what provides the satisfactory oil film between the shaft and the bearing. Okay, that is why in any bearing you have a clearance. That clearance enables the shaft to rise and allow the oil to go underside of the shaft. Now, in hydrodynamic lubrication, to enable that film of oil to go under the shaft, you need 4 parameters to be satisfied. All right. These 4 parameters, the number one parameter is the correct viscosity of the oil. The oil cannot be too thick and neither can it be too thin. All right. So the designer of that bearing, he studies the load, the size, the speed, the temperature at which it works. And using these parameters, he decides on the viscosity of the oil that is to be used. All right. Number 2 is the speed of the shaft. At a certain speed, that viscosity oil will be suitable because the speed enables the oil to be drawn to the underside of the shaft. Oil has an affinity for metal. In other words, if I pour oil on a steel surface and I wipe it off, it doesn't mean all the oil has been wiped off. But if I pour water and I wipe off, all the water gets wiped off. So steel or metal has an affinity for oil. And this principle is used for all machines. So when the oil falls on the steel surface and the steel shaft rotates, it drags the oil down to the underside of the shaft. And this is possible if the viscosity of the oil is right. If the oil is very thin, then the oil will get squeezed out from the sides and will not be drawn in. If the oil is very thick, it will not even go inside that gap. So that viscosity is the most important criteria for that oil which is used for that particular bearing. Second one is the speed. The shaft must have a particular speed to enable that oil to go underside of the shaft. And that speed should not be too slow. If it is too slow, by the time the oil is dragged, it will get pushed out. So the time is a factor. So that means speed makes the difference. So you have viscosity and you have time. Third factor is the clearance. How much clearance is provided for that bearing will enable the shaft to rise and allow that oil to come underside of that shaft. If there is no clearance, then the shaft cannot rise and the film of oil cannot form. So that is the third one. The clearance has to be satisfactory. And the last but not least, you may have a fantastic bearing, you may have fantastic lube oil, you have had all the clearance, but you cannot afford to load the bearing more than its designed load. An overloaded bearing will fail. So that load has to be within certain specifications. All right. So these are the 4 factors. If you want, you can write it down. In time, when I get a chance, I will draw the diagram and I will show you how an oil wedge formation is required to enable hydrodynamic lubrication. But remember, for any bearing, any journal bearing in particular, four parameters are essential. Number one, viscosity. Number two is the speed of the shaft. Number three is the clearance within the bearing. And number four is the load. You cannot afford to overload. It has to be within the design load. So based on these, you get lubrication of the bottom end bearing, the main bearing, the crosshead bearing at the crosshead pins. Now, lubrication on the guides is a little different matter. These are sliding bearings. Similarly, lubrication of the piston ring on the cylinder liner. This is not where you get hydrodynamic lubrication. This is our attempt is made towards hydrodynamic lubrication by profiling the edges of the piston ring, which will give it a wedge form. But that comes a little later. That comes in your lubrication chapter. Let us finish with two-stroke engine and proceed into medium speed engines. What we are doing right now is understanding the basic concepts of the three types of engines: the low speed engine, medium speed engine, and high speed engine. Thereafter, we'll go into the details of their function, the details of their construction first, then their function, their indicator cards, the power development. All these things will come much later. Let's understand very clearly the constructional details of the low speed, high speed, medium speed, and all these actually. So medium speed engines, most of them operate on the four-stroke cycle. I think all of them actually operate on the four-stroke cycle. There is no medium speed engine which runs on two-stroke engines. There were, I remember on Japanese trailers in the 60s, 1960s, they were using slow speed four-stroke engines, which are not very efficient, not very popular, and today's date they are no longer existent, I think. But you don't come across them much. Now, these medium speed engines are basically of the trunk piston construction. In my earlier diagram, I had told you medium speed engine, this is the trunk piston construction. This can be for two-stroke engines and this can be also for four-stroke engine. What does it mean? It means the trunk of the piston, which extends from where the rings are till the bottom of the piston, is called the trunk of the piston. And that is the trunk part which takes the lateral thrust when there is an angularity of the connecting rod. The piston gets a vertical force, no doubt, but that force is ultimately translated into an angular force. This angular force is passed through the connecting rod, and this angular force is maximum when the piston reaches its mid-stroke position, because that is the time when the angle is maximum, and that is the time when the transverse component of the force is also maximum. And this transverse component is taken up by the wall of the piston against the wall of the liner. So this transverse thrust is called the lateral force, and it is reason for getting oval wear down of the cylinder liner. So the cylinder liner, when it wears down, when you measure the bore, you will find the port, starboard, and forward aft directions have different readings. It does not wear down in a uniform circular mode. So that is your trunk type of engine. This trunk type of engine can be two-stroke, can be four-stroke. So don't block your mind about two-stroke being only a crosshead type of engine. But trunk type of engines for two-stroke is very rare, very rare. It is existent, it has been there, and it is mostly on two-stroke petrol engines. Small trunk type diesel engines are very rare. Okay, so let's move on to where we left off. So let's go back. So that is the trunk piston construction. That is your medium speed engine. Smaller and lighter than the low speed two-stroke engines. Obviously, you could get an idea of the sizes, that the parts are much smaller, the components have lesser weight, so they are easy for transportation. A lot of shipping companies prefer medium speed engines instead of two-stroke engines. It's a balance, it's a fight between the two. Your sense of understanding will give you the option of choosing between a medium speed engine or a two-stroke engine for your propulsion purposes. The bigger size medium speed engines are also used for propulsion. I don't remember, but one of the sections I told them to study W64 engine, Wärtsilä. It is the largest medium speed engine and it gives power as much as your large two-stroke engine. So if you have a piece of paper and pen, please write down Wärtsilä W64 engine. Do a little read up on it.
Last time you told us only.
Okay, okay. Have you done any studies on that? Or it is
Yes,
just a note on a piece of paper? Okay, let's move on. The bigger size mainly are used for propulsion. So these big medium speed engines are also used for propulsion, but they require reduction gearing to get the lower RPM. Understandable. If a medium speed engine is running at 400 RPM, a large propeller cannot run at 400 RPM. It has to be below 100 RPM. So you need 1:4, a reduction gearing. The advantage is the ship owner can choose a medium speed engine. The shipyard will choose the propeller depending on the dimensions of the ship, and then the ship builder will decide what is the best suited reduction gearing. So there is no separation of the two. They can be connected by means of a reduction gearing, and the ship owner can choose his medium speed engine. Whereas in a two-stroke engine, the size of the engine, the RPM has to correlate with the propeller. So the propeller and engine has to match each other. In the case of a medium speed engine, you need not match. It is the reduction gearing that will help to match between the engine and the propeller, both sides. All right. Most of them are used as auxiliary engines for electricity generation. That means your generators on board the ship will be all medium speed engines. These engines may be inline or in V-form construction. All right. Now, V-form is something you have already heard of. It is nothing new. And before I go into further, I found a very nice diagram for you boys to take a snapshot and keep for explaining the four-stroke principle. This diagram is very elementary to memorize, very elementary put down. And if you understand it, you don't even need to memorize it. You will simply put down what the parts are. Now let's have a look at this diagram. You need to memorize only two diagrams and the remaining two become automatic. Let's have a look at it. So here it is. This is the explanation of the four-stroke sequence of operations or four-stroke cycle. First is the intake, then is compression, then is expansion, and then is exhaust. These are the four sequences of operation. Now have a look at the diagram. The liner is the same in all the four. The fuel injector is same in all the four. The inlet valve is open in the first case and it is closed in all the remaining cases. The exhaust valve is open in the last case and closed in all the other cases. So it's quite simple to understand. Inlet valve is open only in the first case and exhaust valve is open in on the last case. So all other cases it is closed. Now the first diagram, the angle of the crank is the same as the angle of the crank in the third diagram. So the position of the both the pistons is the same. Only difference is in that this is the intake stroke. The piston is coming down. All right. In this case also the piston is coming down, but it is an expansion stroke. Similarly, in the other two diagrams, both are going up and one is in the compression and one is in the exhaust. So it's very easy to remember so long as you remember intake, compression, expansion, exhaust, and the diagram is very easy to follow. All right. In the case of intake, the inlet valve opens, the piston is coming down, so the air fills up. In the upward stroke, after it has completed part of the after it is past the bottom dead center, while it is going up, it will compress the air and compression stroke. Similarly, after it crosses the TDC, the piston starts coming down, that is the expansion taking place. The hot gases are pushing against the piston, it is being forced down. And finally, again, after it turns around and crosses the BDC, it is moving up to discharge all the residual gases. So take this diagram down, and if you are required to ever explain the sequence of operation of the four-stroke cycle, this is your easy answer. All right. So let us move on. Let us see an engine. I had told you in the last comment, maybe inline or V form. So this is your inline engine where the units are all vertical and all the components are shown in labeled form. So this is your what you call your connecting rod. This is your crankshaft. There is the counterweight on the crankshaft. This is your crankcase relief valve. If there is overpressure inside the crankcase, this relief valve is allowing the exhaust pressure to release. There is a protection plate on the outside, if you notice, so the gases will not blow out just straight out like that. Because if you happen to be standing over here, the hot flame and a gas might hit you. So it is allowed to come downwards in this direction. So this plate here is a protection plate which allows the gases to come down. It is a spring-loaded valve and allows the excess pressure to build in to come out. Oh, Ruth Raj has a question. Excuse me, sir, my mobile battery is getting low. Shortage of electricity since morning. Oh, I'm very sorry about this, Ruth Raj. I don't know how. At least if you had electricity, you could have put your phone and charging while you're listening. Anyway, we will share this lecture with you.
Excuse me, sir.
Yeah, go ahead.
It's yes, sir. I am living in village area, so there are the thunderstorm and lightning last night, sir. So shortage of electricity, sir. So we can't live or more online.
I'm feeling very bad about this. What to do? Anyway, we will share the lecture with you after the class is over. Do go through the entire lecture, including what I am saying. There are a lot of things which I am saying which are not in the PowerPoint plates, and they are nuggets of information which come to my mind while I explain the engine. So be sure to follow up on the lecture at a later date. All right. Okay, Rudraj, we hope you can come back to class if the electricity comes out. Okay, let's move on. The difference between piston and connecting rod. Hey, come on, Shankar. Okay, never mind. Good you asked. Doesn't matter, you asked even. See that diagram I showed you, the piston can be connected directly to the connecting rod. All right. And if it is connected to the connecting rod, it will be a trunk type of engine. Where is the trunk type of engine? Oh, yeah. See, the piston over here is connected to a rigid rod. That is the piston rod. And it is rigid. In that video also, they showed you a piston upside down. And the rod is rigidly connected to the piston rod. And then you have a connecting rod which may or may not be connected to the piston. In the case of a trunk engine, there is no piston rod. There is only a connecting rod. He's written something wrong over here. This should not be piston rod. It is called a connecting rod. This connecting rod is connected to the crank pin to the piston. All right. This over here is a piston rod. This here is a connecting rod. This connecting rod has the same function. Over here it is connected to the gudgeon pin. Here it is connected to the crosshead. Actually, these diagrams I have taken from the net, and there are a lot of mistakes in the net diagrams. And once you take a diagram from the net, it is very difficult to do the corrections. This is not a piston rod. Here, written here, piston rod. It is a connecting rod. Please, I don't know how to correct this also. And there are other places also, there are some small errors. And those errors are not possible to correct because they are coming from the net. But remember, this is not, I don't know how to correct this. It is supposed to be connecting rod. Like here, this is also a connecting rod. This here is a piston rod. In the trunk type of engine, I can understand now why Shashank Shekhar has got a question like difference between piston and connecting rod. It is because of this error here. Here understood as a piston rod. This is a wrong term to use for this rod. This rod is a connecting rod. All right, Shashank. Now your question is very justified.
Yes, sir.
Okay. Now, are we calling the rod which connects the crankshaft as a connect? Yes, we are calling the rod which connects the crankshaft to the gudgeon pin or the connecting rod which is connecting the crankshaft to the crosshead as connecting rod. Con rod. The short form is called con rod, and that connects either to the gudgeon pin of the piston to the crank or from the crosshead to the crank. These are all connecting rod. Piston rod is something that is fixed rigidly to the piston. This is the piston rod. This is not a piston rod. See, he's written piston rod here also, piston rod here, and he's not made a mention of what rod this is. Yeah, here he has said crankshaft and connecting rod bearings as well as crosshead guide are lubricated by the system. If we can call this connecting rod, why he has called this piston rod? Doesn't make sense. So be careful. Do not take everything from the internet as gospel truth. All right. Okay. I hope that explains your doubt. It is good that you asked that question, because some of these internet diagrams I've copied from the internet. They are not correct. Let's move on. Otherwise, we'll not finish. Okay, so this is your inline engine, and it has got all the parts. Now, the parts are so small, I can read them. Yeah, they are more or less okay. This is the exhaust valve, and this is the inlet valve. All right, now he's got the rocker arm over here. This diagram seems to be okay because this is actual drawing of an engine. But this other diagram, which I showed, trunk engine, is not a diagram of an engine. It has been drawn by a professional and then put over there. But this diagram is a direct engine diagram to proportion, correct proportion. So this is a crankcase relief valve. This is your crank pin, and this is your crank web, etc. Take a look at this simply. Just my intention was to show you inline diagram. Next, what we are going to show you is a V form of an engine. The V form of an engine is also used as diesel engine. Only it is here. This is a V type of engine, and the angle can be anything from 45 degrees to 90 degrees. Only difficulty here I found, or rather only item that you need to ignore, is this spark plug. This spark plug. Actually, this is a petrol engine, and this spark plug is intended for, imagine this as a fuel injector, and then everything will be the same. There will be no difference. So here is the V-type engine, and the two sections that are shown is one through the inlet valve and one is through the exhaust valve. So there are two different sections which are being shown to you. If you see, the inlet valve has the air passage coming in from here. It comes from here, passes through the inlet valve and goes into the cylinder. And in this case, if you see, that is the exhaust valve. When the piston goes up, if this valve opens, it is discharged from here. Okay, so they are shown in two different sections. In this section, the exhaust valve has been cut through, and in this case, the scavenge valve, or rather, sorry, the inlet valve has been cut through. And what you see is inside the piston, the connecting rod, both are connected to the crankshaft on the same throw, and the connecting rod and the crankshaft has a counterweight here to balance the crankshaft. Inside the crankcase, you have an oil pump. This is called the lube oil pump. This oil pump draws the oil from the sump. In the medium speed engine, the oil is contained in the bottom of the sump. In the two-stroke engine, the oil does have a sump, but the oil is not connected there. A pipeline takes that oil into what is called a drain tank. All right. In a two-stroke engine, the oil does not stay in the sump. It is taken into a separate oil tank. An external pump draws oil from there to pump the lube oil to the engine. In the case of a medium speed engine, you have the pump which is engine driven inside the engine, and the oil is drawn from inside the sump itself, and then that oil is pumped to various parts of the engine for the main bearing, crosshead bearing, bottom end bearing, all three bearings. All right. Sorry, not crosshead bearing. There is no crosshead bearing here. It goes to the gudgeon pin bearing. So the gudgeon pin bearing is lubricated by that oil. The bottom end bearing is also lubricated by that oil. The main bearing is also lubricated by that oil. So all these three bearings are lubricated, and the oil which is going to the crosshead bearing is ultimately discharged back into the sump. The oil which is splashing inside will splash against the walls of the engine and allow for lubricating of the cylinder liner. The piston has rings. One of the rings is called an oil scraper ring. This oil scraper ring helps to remove excess oil from the cylinder liner. I told you a little while earlier that if you throw oil on a steel surface and you wipe it off, it doesn't mean that all the oil is wiped off. A little oil will remain. So even when the oil scraper ring on the piston scrapes off the oil, there is still some oil on the surface, and that is adequate for the piston ring lubrication. It is the excess oil that splashes on the liner that is scraped off. Otherwise, what will happen? That oil will gradually be going up above the piston rings and into the combustion chamber and get burnt out with the gases. All right. So this is a V-type engine, and this can be a diesel engine, but without what you see is a spark plug. This should be a fuel injector here. Otherwise, it is the same. Okay. So this is the profile of a V-type engine, and this engine, large V-type engines are also used as your propulsion engine. I have had this peel stick engine on one of my ships, and it was a very good engine. Peel stick is made by a French company, so engines are good, nothing wrong with it. Now, other than inline and V-type, you have the other forms of engine which are used on shore. So this is your inline type of engine. This is your V type of engine. This angle seems to be more than 90 degrees. So this is just a sketch. Remember, I have not seen angles more than 90 degrees. This angle seems to be more than 90 degrees. So which is actually a diagram not taken directly from an engine picture. This is an opposed piston engine, and this is a radial engine. If I remember correctly, these engines were used during Second World War for aeroplanes. So they had multiple cylinder engines all around, and that was used to run the propeller of the aeroplane. I have not seen these engines anywhere else. So our requirement is to understand inline engines and V-type engines. Okay. Okay, let's go on. Next, what we have is high-speed engine. They are all engines which can be also V-type and inline type. Both these high-speed engines can also be V-type. So the first thing is, it is rarely used on board except in some cases as auxiliary diesels and emergency generators. Yes, emergency generators run at higher than 1000 RPM, and they are using a very high grade of oil, which is actually high-speed diesel. So they can be used on board, and they are usually emergency generators. Your emergency compressors may also be using a high-speed diesel engine. Apart from that, your lifeboat engine could be a high-speed diesel engine also. They also operate on the four-stroke principle with VGT. Now, a few words about this VGT. Modern engines are using the VGT. VGT means variable geometry turbocharging. Sometimes it is called VTG, variable turbine geometry. What is it about? Now, you see, when you have turbocharging of an engine, that turbocharger is basically a freewheeling machine. In other words, it does not have direct connection with the engine. It is not chain driven, it is not gear driven, and neither is it shaft driven. It is only the exhaust gases which emerge from the engine that are blowing on the blades of the turbine. All right. So there is no mechanical connection. Only the exhaust gases which are blowing on the turbine causes the turbine to rotate. And on that same turbine, on the same shaft of the turbine, you have another blower, a fan. So the moment you blow air on the turbine, obviously the blower will also rotate. And that blower will draw air and put it into the air inlet of the engine. So the air supply to the engine is coming through the turbocharger. Okay. Now, when you start the engine, there is hardly any exhaust gas. All right. So there's hardly any exhaust gas that the turbine will not pick up any speed, or it will take some time to pick up speed. And during that time, there will be hardly any air supply to the engine. If there is a shortage of air supply, the combustion will not be satisfactory. So part of the fuel will burn, part of the fuel will not burn. It is only when the turbine can deliver more air through the blower, then only the engine will pick up speed. isn't it? You can give more fuel, but that's no good unless you give more air. To combat this situation, especially under part load conditions, or to improve the acceleration of the engine, we have what is called variable geometry turbocharging. When the engine is running at part load, it is not getting enough air because I explained to you. Now the exhaust gases which is emerging at a slower speed. All right. Now if it is passing through a large diameter pipe, then the flow rate of the exhaust gas is small. Now if I taper that pipe and make it into a small passage of exit, then the path of the gases passing through that part will be much faster. And thereby, if that is now directed toward the turbine blade, the force to rotate the turbine blade becomes higher. So the turbine will become much faster and faster in its rotation if you narrow the passage of the exhaust gases leading to the turbine. All right. So the moment you have an increased speed of the turbine, you automatically deliver more air to the engine. So variable geometry turbocharging is an arrangement which reduces the nozzle to the turbine blades wherein the flow of gases is directed. All right. This is a mechanical device and it is dependent on the load. So the opening of the nozzle can be increased, it can be decreased. And this process is called variable geometry turbocharging. Again, under part load conditions, you don't get enough air to the engine. To improve the air supply to the engine, we need to speed up the turbine. Now, when the engine is delivering hot gases to the turbine, if the nozzle through which the hot gases are passing and are directed to the turbine blades, if they can be narrowed, then the flow of the exhaust gases becomes faster. If there is a faster flow of gases through those narrowed nozzles, then the turbine gets a bigger torque to rotate at a faster speed. The moment the turbine rotates at a faster speed, the supply of the air to the engine also improves. So this process of improving turbocharger performance during part load conditions is called variable geometry turbocharging, or sometimes it is referred to as variable turbine geometry. Is it understood? Sarthaki, are
Excuse
you
me.
hearing?
Yes.
Okay. Okay.
Yes, sir.
Okay. Let's move on.
Excuse me,
You
sir.
can, yes, what is it? Yes.
Sir, can you please explain why we don't have proper amount of air during part load? I'm still not able to
In a
understand
in
that part clearly.
okay. In a turbocharged engine, where is the supply of air coming from? From the blower. The blower draws air and delivers into the engine. All right. So if the blower is not able to draw air and deliver to the engine in enough quantities, the combustion will not be satisfactory. Understandable. So actually a turbocharger is intended for an engine when it is running at full load or above 75% load. Then the engine is really performing its best. But under part load condition, that turbocharger is useless. It is not performing the function. To improve the turbocharger under part load conditions, you have variable geometry turbocharging. All right. Hello.
Yes, sir. Yes, sir.
What?
So now
Hello. How
sir,
it works?
now it's clear.
Put your question clearly. What is it that you don't understand?
Sir, I was not able to understand why we are not supposed why we are not getting proper amount of air during part load. But now it's clear, sir. It's because of the
Okay.
turbocharger.
Yes, because of the turbocharger is in a normally aspirated engine, the suction is open to atmosphere. But in a turbocharger engine, it is the blower that is supplying air to the engine. And if the blower doesn't supply, the engine doesn't get the air. And engines will perform with turbocharger very well if the engine is running on 75% or more on load. That is why you must never run an engine under part load conditions. It is more damaging. Or you must never run the engine on overload condition. You must run it on full load condition. Then it is running in very good health. The health of the engine will remain satisfactory if you run it on 75 to 85 to 90% of load. Okay.
Excuse me, sir.
Yes.
So why can't we use supercharger instead of turbocharger?
Of course, you can use the engine that we have in our workshop is got a supercharger, and there are so many other means of supercharging. Turbocharging is a means of supercharging, but supercharging does not necessarily mean turbocharging. Be careful. Turbocharging is a means of supercharging, and it has been found to be the best because it does not draw any energy from the engine. The other modes of supercharging, they extract energy to work to deliver air to the engine. So ultimately, overall efficiency is going to drop. Turbocharging is purely waste energy from the engine being utilized. Other forms of energy are using the engine energy to run to allow more air into the engine. There lies the difference. Is it clear?
Yes, sir.
Okay, let's move on. The fuel used is a high-speed diesel. That means for these high-speed engines, you cannot afford to use LDO, marine diesel, or residual fuel or heavy oil. They have to use good quality oil which combusts very rapidly because the piston moves up and down very rapidly. So the time for combustion and completion of combustion is very small. So the fuel oil has to be very, very combustible in the sense it must have very little delay in burning and completing combustion process by the time the piston reaches its bottom dead center. Okay, so this is usually high-speed diesel. So this is the same diesel oil that we use in our diesel cars that are there on the road. Okay, high-speed engines are used in small vessels with or without reduction gears. Sometimes the high-speed engines, they are directly coupled to the propeller. These propellers are made of stainless steel, and their pitch, their diameter, their specifications are matched to allow for high-speed rotation. So in high-speed engines, in small patrol boats, speed boats, they are using these high-speed engines, and they get directly driven from the engine. No reduction gears required. And if you must know what is the fastest speed of a vessel moving on water, is something like 105 miles per hour. That is almost 150, 60 kilometers per hour. There are speed boats which are of that speed. Do look up on YouTube. You will get some of those speed boats. They are made as if they are like rockets. So all the safety factors have to be taken into consideration, but they are used for sport. They are not used for any commercial reasons. Okay, high-speed engines cannot be run on residual fuels. That is the thought of today, all right? When we were in your position, when we were students, we were told medium-speed engines can never run on heavy oil or residual fuel. But time, demand, and necessity has changed that concept. And today, medium-speed engines are running fine on residual fuels. At that time, it was unthinkable. And today, running high-speed engines on residual fuels is unthinkable. Maybe 20 years from now, it'll be a reality. So don't keep your minds blocked, because that time we kept our minds blocked against residual fuels being used for medium-speed engines. But now, I have started to be a little more flexible in thinking that maybe someday high-speed engines will also be running on residual fuels if the technology can be provided. So as of now, high-speed engines cannot be run on residual fuels. Okay, let's move on. What are the uses of these different engines? We'll go through this fast. Main propulsion engines, they are used as, low-speed engines are used as main propulsion engines for ships. They can burn low-quality fuels, and power plants also use them for power generation on shore. Yes, there are power plants in our country which are using huge, massive two-stroke, large-bore diesel engines for generation of power. These are private organizations which provide power to industries. It is not necessary that only state government bodies can provide electricity. There are private power plants which give power at costs which I don't know, but they do provide. I had the experience of going to one GMR industry where they were providing power. They had just one engine, 12 cylinders, and one of the largest engines I've seen, much larger than what you see on the ship. And 12 cylinders means it's a long engine too, which cannot be permitted on the ship because the ship has to have certain amount of flexibility. So the engine will also start having flexibility during hogging and sagging of the ship. So you cannot have a very long engine on board a ship. So this particular engine was a 12-cylinder engine, and it was providing 50 megawatt power to the industry. And that was where we had gone to give a lecture. They were having problems that it could only produce 48 megawatts. So the owner was complaining that he was not getting full return of his investment. He wanted 50 megawatt power output. So we had gone to help him out. Not that we had much of success. We could just barely get 0.5 megawatt more than what anybody else could get. Anyway, that's another story. But keep in mind that large engines are also used on shore for power generation, and they're two-stroke engines. The alternator I found was as large as diameter was as large as a two-stroke building. It was not long, but it was diametrically large, and the length was about, say, as long as a truck. How much is that? 20 feet? 20 feet width, and about diameter of a two-story building. Medium speed engines are usually used as auxiliary engines for power generation on ships. They are also now used as propulsion engines with the help of a gearbox. So the gearbox is essential because the medium speed engine RPM is much higher, and the propeller which is used to run that big ship will be large in diameter, and the RPM will be much smaller. Efficiency of a slow-moving propeller will be much higher. Otherwise, what will happen? The water will simply churn in place without getting the requisite thrust. Whole purpose is lost. And it is used for power generation on shore. That is common. A diesel-electric engine, a diesel-electric ship will have multiple medium-speed engines, maybe 6, maybe 8, but all of them are generating only electricity. That electrical power which is available is ultimately used for everything. Your lighting, air conditioning, running pumps, whatever there, including running your propeller. So those are diesel electric ships. Your propeller is run by a synchronous motor, electrical, and control is very, very smooth and almost to perfection. Somebody has a question. Is there any fixed firing order in an inline engine? If yes, what is it? There has to be a firing order of the engine. It depends on the crankshaft positioning. In other words, there has to have some balance. Suppose a 4-cylinder engine, it might be 1-3-2-4 or 1-4-2-3. It can be anything. It depends on the designer, and they will calculate the mechanical balancing of the entire components before they allocate a firing order. It can be 1-3-2-4 or 1-3-4-2, can be 1-2-4-3. It depends on the design of the engine, and that firing order is based on maintaining balance at the RPM at which it is going to run mostly. All right. Now, here comes another issue. You are touching on a point, what is called critical RPM. So right now, we'll keep that away. We'll answer only the question. There is a fixed firing of an engine, and it is dependent on the design of the engine at which it runs. The objective is to keep a balance of forces during firing so that there is no excessive vibration. Next. Siddharth Kesri, your question has still more corollaries. So we will come to that at a later date. Next is, sir, you said very big engines are not allowed on ships. What about Wärtsilä 14RT engine which has 14 cylinders. Okay, the cylinder diameter must be much smaller than compared to these very large engines and we're having 12 cylinders. The objective is that the bed plate on which the engine rests should not have too much of hogging and sagging. That is why long engines will not be permitted. If you see 14 cylinders, the length will be much smaller than the 12-cylinder engine whose diameter of each is very large. So you have a long engine on a ship and which is going to hog and sag, that bed plate is going to be in trouble. Get it? 2.5 meter piston stroke. What is the diameter? What is the bore? Stroke is vertical movement. You check out the stroke bore, 96 millimeter. These are more than 1 meter, the ones that are out on the shore. Okay, they must be using, it must be more than 1 meter is the diameter of the bore of these engines, which are on shore. I've never seen 14-cylinder engines on my ship. Must be more recent development, and they will require extensive strengthening of the bed plate, extensive strengthening of the hull of the ship where the engine is located. Otherwise, the engine is subject to, rather, the ship is subject to a lot of hogging and sagging, and that will cause bending of the engine also. So that is why there will be some restriction to serve Wärtsilä 14RT engines. 14RT engines.
So
Are
you
they
told
used?
about that W64, so I came across this.
I'd like to know which ship has got this. The ship's particulars must be entirely different. All right, you're keeping up to date. That's good. That's nice. So let's move on. I want to finish this PowerPoint. It's already 10:35. So medium speed engine, auxiliary power generation, gearbox used for power generation on shore. Emergency generators, compressors, lifeboat, high-speed boats. Emergency generators are used with, they use high-speed engines, but our work with high-speed engines will be very limited. Normally, emergency generators, we never overhaul. The entire job is done by shore staff. So if at all the emergency generator is taken ashore, brought back after overhauling. So that's the way it is. And emergency generators don't run so much. So the possibility of sending it for overhaul is once in 10 years, maybe. Once in 10 years, once in 12 years, once in 8 years. Because it is only run during an emergency and for a short period. So the utilization is very spare. Okay, let's move off. Who are the manufacturers of four-stroke engines? I had told you the manufacturers of two-stroke engines are basically three corporations. There are one or two more, but they don't have much of a market. One is, I think, Gotaverken, which is a Swedish company, and one is, I think, Harland and Wolff. These are one or two companies, but not of much significance. The main three are the Mitsubishi, Burmester Vane and Sulzer, Burmester Vane and MAN, Sulzer and Wärtsilä. But four-stroke engine manufacturers, there must be hundreds. They are in hundreds. I have given a few of the names which are more prominent. There may be a few more. I have not mentioned Kirloskar here. Kirloskar is our own Indian manufacturer. But Kirloskar also originally started with designs which are copied from foreign companies. There is almost no engine that we have actually designed from scratch. All engines are licensee manufacturers or modifications of the existing engines which are mostly developed abroad. We don't have so much of research and development regarding engines in our country, but other countries do have a lot of it. So manufacturers of four-stroke engines, Sulzer by itself makes four-stroke engines, MAN, Wärtsilä, B&W, Daihatsu. Daihatsu is again Japanese. Mitsubishi is Japanese. Caterpillar. Pilstick is French. Akashaka is also Japanese. Deutsch is German. Then you have the Rolls-Royce Group, which is British. Under them, they have given licensee manufacturing to Allen, Berger, AMS, Bandoin, Callison. Allen is the company which is the manufacturer of our engine in our workshop, in our college. And that was built in 1954, which is as old as me, or a little younger than me, in fact. So Allen engine is the one we have, and it is working fine. And the components are excellent quality, but it is now outdated. Outdated in technology, outdated in its efficiency, performance, everything. We have better quality engines which are providing much more with a better heat balance. Okay. Next is Bandoin Callison. Bandoin is Spanish, Callison is Italian. So they are given licensee to all the other countries. Deere, Detroit Diesel, Electromotive, Hanshin, Hedemora, Isuzu, Japanese, Iveco is I think Swedish. Swedish, yeah. Hedemora, Isuzu, oh, Isuzu is reported. No, Isuzu is one. So Lugger, Makita, Mitsui, MTU, there are so many. So don't block your mind about four-stroke engines. The sky is the limit for manufacturers for four-stroke engines. Next, practical heat balance diagram. This is now an important part in understanding the thermodynamics of an engine. The diesel engine has high thermal efficiency and low fuel consumption as compared to any other form of engine or prime mover. That is very true. That is why it is still lasting. The heat balance of an internal combustion engine indicates the heat that is rejected to jacket cooling water, turbocharger jackets, lubricating oil, after cooling, that is in the boiler, radiation. Heat energy to provide power is the only one that we are getting as a benefit for the engine. Other than that, all the other heat that is developed on burning the fuel is lost or utilized some other way. Then air cooling, lost to atmosphere. Now, the heat balance diagram is indicative to show you where is the energy from the fuel going. Part of the energy is used as work contributed by the engine, and a good part of the heat energy is used for other purposes. Now, the other purposes is, one thing is turbocharger is using some of the heat energy from the exhaust gases. After the turbocharger, the exhaust gases go to the boiler, and then the boiler uses some of the heat energy. That is one. Another source of utilization is the cooling water, which is used to cool the engine, becomes hot. So the heat in that cooling water is again used in a freshwater generator. So you can generate fresh water from seawater at no cost. You understand? So that is also used on board the ship. Apart from that, the cooling water which is used for cooling is then thrown overboard, which means some of the heat energy is lost there. Then you cool the engine with air. So some amount of heat energy is lost there. Then the radiation from the engine is also coming through. So that causes some amount of heat loss. Now, all these losses are indicated by the heat balance diagram. To have a very authentic and very clear heat balance diagram, you need to have prior information on the engine that is running and burning a particular fuel. So what is the information required of the engine? Number one, the size of the engine, that is the bore and the stroke one. Number two, the fuel consumption per unit power that it is developed. That means specific fuel consumption rate. That has to be known. These are the two parameters that you need to know before you can actually draw a heat balance diagram. The heat balance diagram is intended for an engine with specific details. You cannot have just general. So the specific details is the size of the engine, the stroke and the bore. And second thing is the fuel consumption, how much it consumed per unit of power developed. Okay. The second item that you need to know is the fuel that you're burning in that engine. What is its calorific value? That means how much energy does it have per unit mass? Based on these two parameters, you can make out your heat balance diagram. Otherwise, if you make a general heat balance diagram, it makes no sense. So the next picture I am showing you is, here. Figure shows a typical heat balance diagram for a modern high output engine, and the figures over here are indicative of the bore and the stroke. All right, this bore and the stroke indicates the size of the engine, and it is also a turbocharged diesel engine, and based on a specific fuel consumption of 226 grams per kilowatt hour. The fuel oil heat value or the calorific value is 42.6 megajoules per kg. These are the parameters you need to know before you make a heat balance diagram showing you 10% goes here, 17% go here, 20% go here, 13.5% goes here. How can you decide on these? So these are the parameters required. Any heat balance diagram must correlate with engine performance, fuel consumption, and calorific value of the fuel used. This is the bottom line. Any heat balance diagram must correlate with the engine performance, fuel consumption, and calorific value of the fuel used. Now, I have made out a heat balance diagram, which is from a technical paper from Institute of Marine Engineers. So they have actually taken the values from the engine and presented it in a more authentic means. Now, here is that diagram which I have made and scanned. Let me make it a bigger. Okay. Now, heat balance diagram, the specifics is engine is 356 into 457. This number means bore and stroke. Remember, bore is always larger than stroke. When you talk about stroke to bore ratio, that is a different matter. All right. But an engine which is given with figures like this, engine 356 to 457, then you say that it is 356 is the bore and 457 is the stroke. The stroke will always be larger in a diesel engine as compared to any other engine. Petrol engine may have a square engine where the bore and stroke is the same, or the bore may be larger than the stroke. Racing engines, they have strokes which are shorter than the bore. Okay, fuel consumption is 226 grams per kilowatt hour. The fuel heat value is 42.6 milligrams. Based on these parameters, you have a heat balance diagram which says the input is 100% and the work output is 37.4%, which is quite pathetic. But then that is it. The stack losses. Stack losses means what is going up? The stacks. Recoverables, which is amounting to boilers, etc., and where the heat energy can be recovered. Air cooling causes a loss of 4.77% of that energy. The radiation loss is about 4%. The heat loss to the cooling water in the engine jacket is so much. All right. But I suppose not everything is lost because part of it goes into the recoverables here. Okay. Next is the turbine jacket, because that is also losing heat. Sometimes you have a cooling water on the turbine jacket to cool it. And some of the modern engines now have done away with it. They don't cool the turbine. They let it run very hot. They have an insulation provided so that the engine room personnel don't go and touch it. But thermal efficiency is improved if you don't have this loss from the turbine jacket. So 2% if you can gain, you can increase this to 39 or even 40%. So turbine jacket sometimes is insulated. We had a situation on board where it was cooled with water and then cracks started forming. So we called the expert from Sulzer, main Sulzer company in, it was a Sulzer turbocharger. And expert came and he told us, stop putting any water for cooling and introduce these pellets. So he bought pellets made of clay. They were porous pellets and he filled the space where cooling water was with pellets. And he kept the bottom window open, top window open. So there'd be a natural draft of air allowing those pellets to be cooled. And we stopped cooling the turbocharger. And the engine was running fine. And in fact, the efficiency improved. So this turbine jacket in the modern engines may not be cooled with cooling water. Okay. And then engine lube oil is also an area where the heat is extracted from the engine by the lube oil and the lube oil passes through lube oil coolers. Ultimately, that heat is discharged to the cooling water and overboard. So where is this heat coming from? Obviously from the fuel that you're burning. So if you keep cooling the components of the engine, these are the losses of energy from the fuel that you're burning. All right. So this is what is the heat balance diagram. and it is showing you what percentage of heat is converted to work and what percentage of heat is lost to various factors which are essential. You can't avoid cooling of the engine, because if you don't cool the engine, it will be overheated and the material will fail. Okay, now this is another diagram I've taken from the net, and it is also showing a heat balance diagram, but it does not have so much of authenticity. Why? Because he has said fuel 100% and the other discharges he has shown as an approximate. But he has not stated what is the specifics of the fuel, what is the engine that is running, and he has blindly said the shaft output power is 49%, 49.3%. Which is not very authenticated, but you can represent it, and this will not fetch as much marks as what you would if you gave the specifications of the fuel and the specifications of the engine. That is way of showing the heat balance diagram. Likewise, you have another one which is a little more authentic because he has given you engine specification, but here he has not given you the oil specifications. What is the energy per unit mass of fuel? This is another way of expressing your fuel or your heat balance diagram. But remember, the heat balance diagram must be supported with technical data. That technical data is the specifics of the engine and the specifics of the fuel. Okay. Next, what you have, let me small this down. Mean piston speed. Now we are coming gradually into the theory of the engines, and my next PowerPoint plate is in the process of being made. It is not yet complete, but I hope by the time next week arrives, it should be ready. The mean piston speed is the average speed of a piston in a reciprocating engine. You see, slow speed engines are slow because the mass of the piston is very high, the size, the mass, whereas a small engine has a very small piston, and that piston is also made of very light material. So the piston can have 3000 RPM. So the piston moves up and down. The forces involved are minuscule compared to the forces involved in a slow speed engine. All right. The piston inside an engine has to accelerate from bottom dead center, reach its maximum speed in the mid-stroke, and then again decelerate to stop at the TDC. Again from TDC, it has to accelerate and come up to the maximum speed at mid-stroke, and again decelerate when it comes to the BDC. Now, during this acceleration and deceleration, if the mass is very large, then the forces involved are also massive. Force is equal to mass into acceleration. So if you have very large mass of the piston, the forces that are involved, that is the forces that the bearings are supporting, are so much that the bearings can fail. So that is why slow speed engines will not have high speed. Simple. What is it? Sengupta has a question. While always presenting a heat balance diagram, do we need to have a particular... Yes, it would give more authenticity to your heat balance diagram. Simply stating 10%, 5%, 6%, on what basis are you suggesting these 10%, 20%, 15% going to losses? On what basis can you say my engine work is 40% or 37%? On what basis? The figures that are given are related to an engine performance and related to the quality of the fuel used. So you will get much more credit if you can explain a heat balance diagram with technical data relating to the engine and relating to the fuel, both. Okay, Sengupta, is it clear? Okay, he has given his clearance. So what I told you, the forces involved in accelerating and decelerating the piston is massive. And the ultimate load goes on the bearing which is holding that piston, isn't it? So the bearing has to take a lot of load. It is not only load for rotating power. It is the forces involved in the moving masses, the inertia forces. I expect you understand what it means. There is a factor of 2 in the equation to account for one stroke to occur in half of a crank revolution and a 60, figure 60 to convert seconds from minutes in the RPM, obviously. For example, a piston of an engine which has a stroke of 90 millimeters, that is 90 upon 1000 meters. You have to convert it to meters to explain speed in meters per second. We'll have a mean speed of 3000 RPM of 2 multiplied by 90 divided by 1000 multiplied by 1000 by 3000 divided by 60. That is equal to 9 meters per second. Now 9 meters per second is about 30 feet per second, which is very fast. You move 30 meters per second, I think it's very fast. So mean piston speed plays an important role in the exchange of gases. Now here we come to a very important point. Now if the piston is moving super fast, very fast, okay, 3000 RPM, the air which is coming into cylinder will only can come at the pace at which it is being drawn under atmospheric pressure, if it is a normally aspirated engine. The flow characteristics of air, remember, is not like electric current. Electric current, moment you put on a switch and the light comes on instantly. So the speed at which the electricity flows is enormous. But airflow is dependent on the density of the air, the passage of the air, the bends and twists of the air, the surface on which the air is flowing over. So all these create a speed of air which is much less than what is electricity. The flow, it is called flow characteristics of air. Now, if the piston is moving too fast, by the time the air can come in fully to the required pressure, the piston has already reached its BDC, and now it is on the compression stroke, so the valves have closed. In other words, the gate has closed. So that is the way the limitation of air can come into the air, into the cylinder. And this is called volumetric efficiency. The piston speed will determine the volumetric efficiency of an engine. That is the mass of air that can come into the cylinder, given a permitted stroke length. We will come into these details in the next class. What is volumetric efficiency? What is Cavendish efficiency? What is mechanical efficiency? What is thermal efficiency? All these. So beyond a certain piston speed, the efficiency of the gas exchange presses drops sharply, thereby resulting in poor combustion. If the air doesn't come in, the combustion air doesn't go out. That's the way it is. So the whole gas exchange process, that means air coming in, gases going out, becomes very poor. The mean piston speed is a parameter in the power equation which suggests that power can simply be increased by increasing the mean piston speed. Right now, you're only touching upon the subject. When we do indicator diagrams and then we calculate the power, then we'll do more details about piston speed. But remember, faster the engine speed, more is the power developed and more is the fuel consumption. Those are fundamental equations. Faster the piston speed, more the power, more the fuel consumption, and of course, more the wear and tear. So that is why a lot of ship owners do not want medium speed engines. They prefer the two-stroke slow speed engine, in spite of it being heavy, cumbersome, difficult to transport, all those questions. Okay. Increase in mean piston speed will increase the dynamic forces and moments, and this will affect bearings, bearing bolts, and the moving components. So ultimately, a piston will have some mass, and if you increase the mean piston speed, the forces will also increase, because ultimately the piston is moving to accelerate to its maximum speed. Then again from mid-stroke, it has to decelerate to a stop position at the TDC. Then again from TDC, it has to accelerate to its maximum speed at its mid position, and then again decelerate from mid position to the BDC. So this continuous acceleration and deceleration forces will exist on the piston. Now, if you increase the mass of the piston, then the forces are going to multiply. And if the forces are going to multiply, the ability to lubricate the bearings which are holding that piston mass or moving part will become very difficult. So you must have light piston. At the same time, it must have adequate strength to take the forces of combustion. So the designer has to consider various aspects of the engine before he can give you a piston to work at certain load and at certain speed. Okay. If the mean piston speed is high, time available for fuel combustion is less. Complete burning of the fuel is poor. Obviously, fuel have a certain speed of burning depending what category and type of fuel it is. Petrol burns very fast. Light speed or high speed diesel burns little slower than petrol. Light diesel oil burns even slower than high speed. Then marine diesel oil burns slower than LDO, and heavy fuel oil burns the slowest. Sometimes it doesn't burn, but you are given to on board that you have to burn it. So designers have started making engines which can burn that poor quality oil which does not want to burn. So they have given it very long strokes, and they have made arrangements to heat that oil to almost burning. Almost just before it starts carbonizing, it becomes like thin oil, and then it is injected. So more important than the temperature that is of the oil that is being injected in the cylinder is the viscosity control. And to achieve that level of viscosity, you need to heat that oil to a certain temperature. Okay, so at that temperature, the oil may start to carbonize. So you have to draw a line up to what temperature you can actually heat it. So it is just below that region where it will start carbonizing, and it will be at its viscosity level equivalent to 10 to 15 seconds redwood, and then be injected into the cylinder. That's the only way it can be burned. And that has found acceptance with a lot of ship owners because it is the cheapest fuel and ultimately improves the profit margin in the transportation of cargo by ships. All right. If mean piston speed is low, now this is the other end of the story. If the mean piston speed is very high, there are a lot of complications. If the mean piston speed is very low, then again there are complications. So it has to be an optimum level. If the mean piston speed is low, that means the piston is moving so slowly that by the time that compresses the air, the heat in the compressed air is lost to the walls and ignition will not take place. So here, mean piston speed is low, compression will be isothermal, but we want compression to be adiabatic. Low mean piston speed will cause compression temperature to be low, resulting in incomplete combustion and increase the fuel oil consumption. So you cannot afford the mean piston speed to be too low, neither is it to be too high. And speed decreases service life of frictional parts. That means parts which are subject to friction, piston rings, cylinder liners, bearing shells, shafts, direct crank pins, crankshaft journals. These are parts which are subject to friction, and the life of these also are reduced. Next is maximum continuous rating. Right now, we are going to do only a part of the maximum continuous rating. In the 6th semester, we will delve in depth on maximum continuous rating. This is the maximum power output of an engine can produce while running continuously at safe limit and conditions. It is the maximum continuous rating. It is regarded as 100% of power and 100% of speed. All right, at normal sailing conditions, and this is decided during sea trials. It is at 100% power and 100% speed. So that point is called the maximum continuous rating or 100% load. It is the maximum power our engine can produce while running continuously at safe limits and conditions. There are two conditions to this. One is safety. It must run safely. There should be no fire in the cabin spaces or overheating of the exhaust pipe or some problem arising by running at the maximum speed. Second factor is it can be run continuously and endlessly. That means for days on it can run without having repercussions. The only problem is the fuel consumption is very high at this part. Okay. So if it is specified example as 100% load as MCR and the speed is 105%, 105 RPM and maximum and MCR power is equal to 14. These are just a example of what is MCR. The engine nameplate and the technical file of the marine engine will be showing these parameters. On the engine we have in our workshop, there is one plate, a label, which is riveted to the engine, and that indicates your MCR and the power available at MCR and the RPM available at MCR under normal conditions. Normal conditions mean the hull is very clean, there is no wind, there is no current, there is no undue loading of the ship. All these factors have to be considered. In normal sea service, we never run it at MCR. MCR speed is at 100% load and is run during an emergency situation. Okay, but it is safe and it can be run continuously. The only drawback is the fuel consumption is much more than what it would be in optimum condition. Its fuel efficiency is less in this case, but it can run safely at this speed continuously. All right. The ship owner does not want you to run your ship at MCR. It wants you to run at a CSR. The CSR is continuous service rating, where you get the best benefit of the engine and at the same time the best benefit of running costs. That means the engine is running in healthy condition. I told you running it in part load condition is very damaging to the engine, but you save a lot of fuel. But that is not required. You will pay in expenses and maintenance of the engine. So that is not safe. So you want the engine to run in good health conditions. At the same time, the fuel also to be in lesser expenditure to the ship owner. So that speed is called continuous service rating. It is also called normal continuous rating. This is the speed that can be considered as the best speed for the engine and ship to run at. The engine remains in good health and the fuel consumption is at the optimum level. Not too low, not too high, but satisfactory. It is about 85 to 95%, or I'll say 80 to 95% is the best. And most of the time, we are running the engines at this load out at sea. And you will see the engines also running in very good health. There is no carbon deposits, there's no carbon formation. All the fuel gets burnt, the scavenging system works fine, the turbocharger is also giving very good air to the engine. This is at 80 to 95% of the maximum continuous rating. Okay. It is the output power at normal service speed corresponding to economical efficiency, thermal efficiency, mechanical efficiency, and easy maintenance. Easy maintenance means no deposits taking place. Otherwise, you will have to decarbonize the engine more frequently. So, continuous service rating is the speed at which you need to run the engine out at sea. It is at this speed the company recommends the ship to run. At this speed, all the parameters are normal and engine efficiency is at its peak. That means it's the best engine efficiency. Okay. I don't know if the sentence has full honesty in it. Engine efficiency and engine power, two different things altogether. So engine efficiency is at its peak, and that is why we run it at continuous service rating. All right. Next, what we have is a typical diesel automotive engine operates around 35% the efficiency. About 65% to 70% is rejected as waste heat without being converted into useful work. That is work delivered to the output shaft. But on ships, we will have some amount of energy from the exhaust gases, recoverables. I showed you in that diagram, recoverables. This diagram shows recoverables as 18.55%, which is a very good feature. And the recoverables are number one, turbocharger. You're recovering energy to pump air into the cylinder, which can burn more fuel and give a higher efficiency. Number two, the boilers. The boilers are using boilers and economizers, same thing. They are called economizers also. So they are recovering the heat from the exhaust gases to give you hot water, steam, etc. Number three, the cooling water, which is used for cooling your engine, can be utilized in a freshwater generator. In that freshwater generator, seawater is passed in, and this hot water is circulated through the seawater in pipes. So the seawater is heated, and the chamber inside that freshwater generator has a vacuum, a state of vacuum. And this vacuum is provided by means of an eductor. The eductor is a device where a pressure at a high water or a venturimeter, same thing, produces the vacuum. So under very low pressure, the boiling temperature of the seawater drops to 40 degrees centigrade. The moment the seawater starts boiling at 40 degrees centigrade, the vapor that is released is condensed, and that condensed water comes out as distillate, which means fresh water. So from seawater, we can manufacture fresh water without any extra cost, and that device is called a freshwater generator. So remember, there are three areas where heat recoverables are taking place after burning fuel in an engine. First is the engine that gives about 37 to 40% of work as your efficiency. After that, you have after that you have turbocharger, then you have the boiler, and last but not least is the fresh water generator. All right. In short, thermal efficiency is equal to work done upon the energy input. It is impossible for heat engines to achieve 100% thermal efficiency. I think that is old hat, old story. And according to second law of dynamics, this is impossible because some waste heat is always produced in a heat engine. The engine itself absorbs some of the heat. If no heat was absorbed by the engine, then we could have converted it to power. But that is practically impossible. So the output is only 40% where you get as efficiency. All right. Okay.
Excuse me, sir.
Yes. What is it?
Sorry to interrupt you, sir, but it's time to move. It's time for us to move to our next class, sir. The next class
Okay. Okay.
faculty is calling us, sir.
Okay, it's already 11:15. You have five
Yes, sir.
minutes to go to the other class.
Yes,
So we
yes,
will
sir.
call it a day. I will stop the recording and we will again have next class. We will go into more
Yes, sir.
minute